Welcome to this explainer. Look, if you're gearing up for the OCR A-Level Computer Science exam, you already know the CPU architecture is a massive topic. Today, we're cutting through all the noise. We're going to demystify exactly what goes on under the hood, focusing specifically on the precise definitions and concepts you need to grab those top marks. So, if you've ever felt overwhelmed by how a computer actually processes information, let's figure it out together.
Here's a super quick look at our roadmap today. We'll start big with the computer brain, zoom into the special-purpose registers and system buses, and then track an actual instructions journey. We'll wrap up with cache memory and a rapid-fire exam prep quiz.
All right, part 1. Let's step right inside the computer's brain.
So, think of the control unit like the conductor of an orchestra. It's a brilliant analogy, right? The conductor isn't actually playing the instruments, just like the control unit doesn't actually process the data itself. But without it, you just have chaos. It directs this massive, complex flow of data, sending out precise control signals so that billions of instructions execute at the absolute perfect millisecond.
Then we have the Arithmetic Logic Unit, or the ALU. This is the muscle of the operation. It handles all the mathematical heavy lifting: addition, subtraction, multiplication. And here's a wild little fact. Division operations are actually way more processor-intensive for the ALU to pull off than multiplication. It also takes care of your logical operations, your Boolean ands, ors, nots, along with comparisons and bitwise shifts.
Moving right along to Section 2, Special Purpose Registers.
Okay, grab your pens, because this exact phrasing is pure gold for the OCR examiners. Registers are temporary storage locations built directly inside the CPU. They are designed for a single, highly specific purpose. And because they're physically baked right into the processor, the access speeds are absolutely blistering. Literally way faster than fetching data all the way from your main memory.
Now this table right here, it's basically an exam cheat code. Examiners absolutely love testing you on which register does what. Let's walk through it real quick. The program counter holds the address of the next instruction. The MAR holds the address the CPU wants to read from or write to. Then there's the MDR, which is literally the gateway. All data coming in or going out has to pass through it. The CIR holds the current instruction actively being executed, and the accumulator? That's your go-to spot for storing the results after the ALU does its math.
Section 3. Let's talk about how these parts communicate using the system buses.
We have the workstations, but we need the roads. Think of the system bus as 3 main electrical highways right there on the motherboard. You've got the address bus, the data bus, and the control bus. Together, they physically shuttle data, memory addresses, and control signals between the CPU, external memory, and your input-output interfaces.
Now, pay super close attention to this because it is a classic exam trap. The address bus is strictly unidirectional. It's one-way traffic only, going from the processor out to memory. On the flip side, the data and control buses are bidirectional. The data bus flows both ways to move actual binary data, while the control bus flows both ways to carry those command signals we talked about from the control unit.
Let's move to Section 4, the instruction journey.
Let's put this all together and watch the fetch, decode, execute cycle in action. It's kind of like a high-speed relay race. First, the program counter copies the address of the next instruction over to the MAR. Step 2, that address sprints down the one-way address bus to main memory. 3, memory finds the requested data and sends it back down the bidirectional data bus right into the MDR gateway. Step 4, that data gets copied into the CIR. And finally, the decode unit figures out what operation to perform, the ALU executes it, and it drops the result in the accumulator. Boom, cycle complete.
Section 5, Cache, and a few extra components.
Another frequent exam pattern asks you to compare registers to cache. I always tell people, think of registers like the pockets in your jeans. Super tiny, single purpose, but you can grab what's in there instantly. Cache memory is more like a backpack. It holds a lot more, but takes just a split second longer to unzip. Registers give you the absolute fastest access inside the CPU. Cache, meanwhile, is graded in levels, like L1, L2, L3, and provides fast access to frequently used instructions. And just to round out your mental model, keep these extra components in mind. They stretch slightly beyond the core spec, but they're great to know. The decode unit acts like a massive lookup table for binary opcodes. The status register flips on and off flags showing the processor's current state. Then you've got the clock, which acts like a metronome, synchronizing everything with constant electrical pulses measured in hertz. And finally, the interrupt register is always listening for urgent hardware or software SOS signals that need immediate attention. All right, home stretch. Section 6, our OCR exam prep quiz.
Let's kick this off with a classic 4-mark question. How do you completely precisely define a register to grab maximum points?
If you want all 4 marks, you literally have to hit these exact key words. 1. Temporary storage. 2. Located within the CPU. 3. Single specific purpose. And 4. Very fast access speed. Get those 4 phrases on paper, and the marks are yours.
Question 2. Guys, people drop an easy mark on this one all the time. What specific information does the program counter hold? The examiner is desperately looking for one specific word here. It stores the address of the next instruction to be executed. If you just write, "it holds the next instruction," you get 0. It's the address of the next instruction. Seriously, don't let them trick you on that.
Last rapid-fire question for you. Which register is strictly meant to store the results of the Arithmetic Logic Unit?
Yep, it's the accumulator. That is your primary general-purpose register for calculation outputs. The mark scheme is super strict here, so just stick with accumulator or its standard abbreviation, and you're golden.
So, as we wrap up this explainer, I want you to step back and just think about this for a second. How is it that billions of these mind-numbingly simple, tiny binary actions, just ones and zeros, zipping down electrical buses from a register to the ALU and back, how do they stack together to create the insanely complex, beautiful software we use every single day? It's just wild to think about. It is a complete marvel of modern engineering, and it's all built on the structured foundations we just talked about. Keep that in the back of your mind as you prep, and keep questioning how the machine really works. Good luck with your studying.